In this lecture, we will introduce a new concept called amortized analysis. So this is a technique to analyze the performance of an operation. So in particular, we are going to give the average time to perform an operation over any sequence of operations. There are three common methods of doing this, namely the aggregate method, the accounting method, and the potential method. So for this lecture, we will focus on the aggregate method, while in the next lecture, we will talk about the remaining two. So let us take a look at this first problem. We call it the superstack problem. So recall that a normal stack, let's call it S, it supports the following two operations, each one of them in constant time. The first one is push. So for push operation, we can insert a certain item, let's call it X, into the stack S. Or we can pop. So the pop operation removes the last inserted item from S. So this is the normal stack. And today we are going to add an extra operation called super pop. So what does super pop do? So super pop is just we are going to pop everything from the stack in one operation. So with one super pop operation, we remove all the items from S. Now the time to perform this super pop is equal to 1, which is always, because there is an operation, so it is 1, plus the number of items that is removed. So it is like a general version of the pop operation. So for pop, so when we are popping an empty stack, so we are still spending order 1 time. And if we are popping a stack which is not empty, then we are also spending order 1 time. So in this case, the super pop is proportional. The time of super pop is proportional to the number of removed items. Okay, now suppose that we start from an empty stack and we perform a sequence of n operations. So these operations could be push, could be pop, could be super pop. We do not know what operations are performed, and also we do not know the ordering of these operations. So we want to analyze what is the worst case time for an operation, and also what is the worst case time for all n operations. Now if we look at the push and pop, they always run in constant time. So actually, if you want to measure the worst case time of an operation, we can just focus on the super pop. And for super pop, the worst case time could be as high as order of n. So how can we get order n? So suppose that we have performed n minus 1 pushes. So in that case, the stack has n minus 1 items, and suddenly we have a super pop. So in that case, we will be spending order n time for this particular super pop. Now, if we are analyzing things in this way, then we know that each operation runs in order n. Yeah, it could be order 1, but then upper bounded by order n always. When we have n operations, the worst case time, we can write it as big O of n squared, because n operations, each operation runs in order n time. Now this claim is actually correct. Yeah, there's nothing wrong. Yeah, because we are just following the logic. Each operation order n, n operations order n squared. But it is not the best bound that we can obtain. So let us take a look of the following better analysis. Now, first of all, the number of removed items in all super pop operations, we will see that it cannot exceed the number of items that are ever pushed on the stack. In order to have removed, so we must have pushed. So the number of removed items in total cannot exceed the number of items that is pushed. But since there are only n operations, the total number of removed items must be at most n. So in such a case, then we will see that the total time that we spend on super pop is bounded by order of n. So the total time spent on push and pop is also order n, because order 1 for each operation, n operations is order n. So it means that if we perform n operations, the time for super pop, push, and pop all together is still order of n. So this is what we see. So in summary, no matter which n operations and in which order they are performed, the total time is at most order of n. So roughly speaking, we can see that, so because we don't care which operations are actually performed, so roughly speaking, we can say each push, pop, or super pop operation runs in order 1 time on average. And formally, in the analysis of algorithm, we call this the amortized time. So amortized time means something like the average out time. So this is the average time. So more formally, so we can say something like this. So for this amortized time or amortized cost, if we say, let's say, after certain analysis, a certain operation, let's call it operation 1, runs in amortized order T1 time, operation 2 runs in amortized order T2 time, and operation 3 runs in amortized order T3 time, then the meaning of this amortized time, amortized cost, is this one. So it means that suppose that we perform N1 operations of operation 1, N2 operations of operation 2, and N3 operations of operation 3, then with these statements, then it means that the total time is big O of N1T1 plus N2T2 plus N3T3. So this is bounding the total time, although there could be some worst case that one operation can take a huge amount of time, but the total time is always bounded by the number of operations of a certain operation weighted by the time that it takes, and then we sum over all of them. So this is what amortized cost or amortized time mean. Okay, so let us take a look of another example. So this is called the binary counter problem. So here we are implementing a binary counter. So a binary counter has a certain number of bits at the beginning, all set to be 0. So this bits is going to represent a certain number in binary format. So at the beginning, because all of them are set to be 0, the counter value is equal to 0. So each time we may perform the increment operation so that we want to make the value of this counter value to be increased by 1. So after one increment operation, the counter will change from all zeros to be 0, 0, 0, 0, 0, 1, something like this. Okay, now for an increment operation, we measure the cost to be the number of bits that are changed. So for instance, let's take a look of the left-hand counter. So this is representing the count 5 because it is 0, 0, 1, 0, 1. So it represents the number 5 in decimal. And after one increment operation, the counter will change its contents to 0, 0, 1, 1, 0. And we can see that altogether, this bit is changed from 0 to 1. And then the last bit is changed from 1 to 0. So in such a case, because there are 2 bits changing, so the cost of this operation is equal to 2. And so we want to measure, suppose that we are going to run this increment operation n times. So what will be the worst case cost for n operations? Now, let us take a look for this one using a naive analysis. So for this, we are going to find out what is the worst case cost for one single operation. Now, because we are performing n operations, so the counter value will be up to the representation of n. So there will only be log n bits involved. So in such a case, the worst case cost for one single operation is order of log n. Because one operation may change up to log n bits, so the worst case cost for n operations will be n log n. Now again, as before, just like the superstack problem, this claim is correct, but it is not the best. So let's take a closer look. So first of all, let us denote the bits of the counter from right to left by B0, B1, B2, and so on and so forth. Now we notice that the last bit is flipped every time. So at the beginning, the counter value is 0, so the last bit is 0. After one increment operation, the last bit becomes the representation of 1, so the last bit becomes 1. And after that, it becomes an even number, right? So the last bit will change back to 0 and 1 and 0 and 1. If we focus on the last bit, it will be flipped, it will be changed for every operation. Now, for the second last bit, let's call it B1, then it is flipped once every 2 to the power 1 operations, which is 2 operations. So at the beginning 2 cases, it is 0 and 0, but after that, it is changing to 1 and 1, and then 0 and 0, and so on and so forth. So in general, the bit bk is flipped every 2 to the power k operations. Or in particular, bk is flipped at the x increment if x is divisible by 2 to the power k. So you can check this easily. So in that case, for n operations, the total cost is, we are going to sum up the number of times each bit bk is flipped. So we are going to sum up for k is equal to 0 up to wherever, so let's say up to log of n. So the bits bk is flipped n over 2 to the power k times. So if we sum all this up, then this will be less than 2 times n. So what does that mean? So for n operations, the total number of times all the bits are flipped is bounded by 2n. So roughly speaking, the cost of each operation, because 2n changes, 2n flips per n operations, means the average cost is order 1 per operation. So more formally, we are saying that the amortized cost for each operation is order 1. Now the previous method for analyzing the superstack and also the binary counter problem, we are doing something that is very similar. We first find out what is the total cost of n operations. So for this one, it is like gathering everything together. So it is something that we call it an aggregation. And once we have obtained the total cost of n operations, we divide the total cost by n. So in that case, we get the average. So this method is the so-called aggregate method.